Good afternoon. So we know that in a given frame of reference, if something is moving relative to us, and then we change that frame of reference, if we start moving relative to the moving object, it is now moving at a different speed relative to us. That is our understanding of the world. Now let's put that in to a physics point of view in terms of inertial frames of reference. Now we are only talking about inertial frames of reference, things that are traveling in in a frame of, not things that are traveling at constant velocity. We got to be careful. We're going to measure the velocities of objects, the positions, velocities, accelerations of objects from frames of reference that are inertial, that they themselves are traveling at constant velocity. So we got to be careful because we can let things accelerate. We just can't let our frame of reference accelerate, the reference from which we're measuring things. So, for instance, if I drop a ball and it falls with an acceleration of g, and I measure the acceleration, velocity, position, whatever, relative to the lab frame, right? Then I am making measurements of an accelerating object from an inertial frame of reference. If instead I get into an elevator, and that elevator is moving up at some constant velocity v0, and then I make measurements of the position, velocity, and acceleration of the dropping ball relative to me moving the elevator. In other words, the elevator has my frame of reference stuck to it. Let's call it is a different frame of reference. Then I'm still, because the elevator is moving at constant velocity, I'm still in an inertial frame of reference, even though I'm making measurements on an accelerating body. So we're talking about measuring things from inertial frames of reference. If we measure things from inertial frames of reference, we know that physical laws should all be the same in any inertial frame of reference. Wait, what did I just say? I just said that we know that physical laws should be the same from any inertial frame of reference. Wait. How do we know that? Well, it was what Newton said, right? Newton said that it doesn't matter whether we make measurements from the lab frame or from a train traveling at constant velocity, that the physics should all act the same. Remember, it was accelerated frames of reference where we had to make up forces that didn't exist. The Coriolis force, for example. I'm trying to think of what some other forces are, but I can't quite. But in any case, it was Newton who said, one of Newton's postulates was that there is no absolute frame of reference. There is no frame of reference that is moving at zero velocity. So all we can talk about is relative motion, right? That the Earth, while it is accelerating, we treat it like an inertial frame of reference unless we have to otherwise. But the Earth is moving. It's a moving inertial frame. It's a moving frame of reference. And so we say, oh, well, I think we talked about this before, but is there a stationary frame of reference somewhere? Is it the sun? No, the sun's moving relative to something. Is it the center of the galaxy? No, the center of the galaxy is moving relative to something. Is it the center of the universe? I don't know where the center of the universe is. I don't think anybody does. There is no such thing as a frame of reference that doesn't move at all. So we need to simply differentiate between frames of reference that move at constant velocity versus frames of reference that don't move at constant velocity. And the ones that move at constant velocity are the inertial frames of reference. And Newton postulated, I mean, it's kind of hard to do science if you say the laws of physics are going to be different for everyone. Right? So if you're in an inertial frame of reference in Lynchburg, Virginia, in the lab, and you're in an inertial frame of reference in London, England, we better have the same physical laws so we can make the same measurements. I mean, maybe we don't, but we do. I mean, we've figured that one out, right? That the laws of physics act the same in all inertial frames of reference. So again, it's simply the frame of reference that we're making our measurements from that must be moving at a constant velocity. That's what an inertial frame is. It doesn't mean that the objects we're measuring have to move at constant velocity. They can accelerate. So I can make measurements from the lab. I can make measurements from a moving train that's moving at constant velocity. I can make measurements from a moving plane that's moving at constant velocity. I can make measurements from a moving spaceship that's moving at constant velocity, etc. That's what we're talking about when we're talking about inertial frames of reference. And this is where we're going to talk about relativity and special relativity. We get to general relativity. Now it's no longer inertial, but we're not doing general relativity in this class. Some notation about inertial frames of reference. Let's say that we've got our lab frame. And our lab frame I'm going to call it the lab frame, give it the coordinate axes X and Y. I'm going to call that O, frame O. And that's what I'm going to call our stationary frame. What does it mean to be stationary? It doesn't mean really anything to be stationary. What it means is we're going to treat that as the stationary frame, and another frame will be moving relative to that. So for instance, let's say that this is, and it doesn't have to be the lab, this is just whatever we're going to call the stationary frame. So let's just say that frame O is the lab frame. And then let's say that I want to talk about a different frame of reference that's moving at constant velocity relative to the lab frame. Let's talk about perhaps a car that's moving at constant velocity, right? Constant velocity. And that car has a different frame of reference. We're going to give it coordinate axes x prime, y prime, and we're going to call it O prime. It's frame O prime. And so our stationary frame is the lab, our moving frame is the car. We could just as well say I'm in the car, and I could call the car my stationary frame. The car is frame O. And say, look, the lab's moving by the car. Right? The lab is moving, I'm in the car. The lab is moving relative to me, so the lab is the moving frame. So it doesn't matter which is the moving frame and which is the stationary frame. We just have to, if we're talking about two inertial frames, we're going to define one as frame O and one as frame O prime. We're going to assume that O prime is moving relative to O at a speed v. It's moving relative to O at a speed v. At a velocity v, velocity v. Constant velocity v, because it's an inertial frame. It must be moving at constant velocity v. So this is just our notation. We have two frames, doesn't matter which one we call stationary, and one is moving at constant velocity v to the other. So if I were to, for example, switch and make the car frame O and the unprimed axis, then the lab would be moving at v in the negative x direction, right? It would be, this car we would say is stationary, and the lab would be moving in the opposite direction. So again, I just wrote it out here. We can switch frames of reference because it doesn't matter which is O and O prime. All motion is relative. They're just inertial frames. The car is stationary, the lab is moving by the car at velocity v. In the opposite direction, then the car was moving relative to the lab. If this was two cars, it would make more sense, right? If it was two cars, then we could talk about one car as being the stationary frame and one car moving forward, or the other car being the stationary frame and the first car moving backward relative to it. It makes sense either way. So let's go back to the original. Where the lab frame is the stationary frame and the car is the moving frame. Okay, and let's just say for the sake of calculating things, we'll see later perhaps why this is true. At t equals 0, the two coordinate axes are coincident. Okay, now think about coordinate axes. I'm literally taking a coordinate axis, right? Take a physical coordinate axis, make it out of wire, make it out of meter sticks, whatever, and just glue it to the lab, just so I can measure things relative to an origin. And then I take a different coordinate axis, again, a three-dimensional coordinate axis, a bunch of meter sticks or some wire or something that just have an x and a y and a z axis, and I glue it to the car. So we're measuring things relative to that origin when we're measuring things relative from the car. Okay, so that's what I've done here, is I've just glued a coordinate axis to the different frames of reference. And let's just say at t equals 0, those two coordinate axes are coincident. That way, we have x equals 0 at t equals 0 in both frames, right? X equals x prime equals 0 at t equals 0. That just makes the math a little bit easier. And then the frames move apart, right? After t equals 0, the frames move apart. Okay. What else do we have to? The whole point of doing this is so that we can make a measurement in frame O, and we can transform that measurement to frame O prime. In other words, we can say, oh, if I measure this in frame O, what am I going to measure in frame O prime? This is what we're doing. So, for example, let's just say that somebody is standing in the lab at a position X. No, we got to give it a different letter. Let's say that they're standing at position S, and S is a distance X initial. Yeah, whatever. is a distance x initial from x equals 0. So it's at a position, sorry, x initial in the unprimed frame, in the frame O. It's called the unprimed frame. So x, according to the unprimed frame, is x initial. At what time is x equals x initial? Let's say the person's standing still, and so x equals x initial at any time. But let's just start with at t equals 0 and later, right? And then remember that O prime at t equals 0 is coincident with O. In other words, their origins are in the same place. And I didn't draw that in this picture, right? I drew one frame of reference slightly ahead of the other frame of reference. But O prime is in the same place as O at t equals 0. So that means that at t equals 0, x prime, the position measured in frame O prime, is equal to xi at t equals 0. But notice, and this is why I drew the axis a little over, at some later time, right? This is at some later time. Let me put something in here, right? So at some later time, this is after a time t, the frame has moved on so that the new position at time t is shorter than xi. And how much shorter is it, right? So at a later time than t equals 0, x prime is equal to xi, but it's gotten shorter by how much? In other words, now I drew over here, I drew a t, but it's moved a distance of what? How far has the frame of reference, the car frame of reference, moved over at time t? This is moving at constant velocity in the x direction, so it's moved over a distance of v times t, distance times time. So that x, the new position at any time t later on, right, right, at some later time than t equals 0, x prime is getting smaller and smaller and smaller. It's getting closer and closer to the person. And then it's going to pass the person, and then x prime is going to get negative, right? So at some later time, at much later time, the car, I didn't give it wheels. The car is way over here, and now the distance to the person is way back this way, right? So it eventually, right, the position x prime gets negative and more negative once the car gets away, right? So because vt is getting larger and larger and larger compared to xi. So the position measured in the moving frame is that, while the position measured in the stationary frame is that. In the stationary frame, I said the person wasn't moving, so x equals xi. In the moving frame, the person is moving relative to the car, and it's moving away from the car, or actually closer to the car at first and then away, but it's moving relative to the car as this equation shows, xi minus vt. Okay, so this is how we transform variables, right? So if we can measure the position in frame O, then we know the position in frame O prime is the position minus vt. Now, this does assume one assumption that we made without discussing, which is that the velocity is along the x-axis. Now, is that a special case or is that a general case? And the answer is, what do you think the answer is? Is that a special case that the velocity is along the x-axis? Or is that generally going to hold true? You might say, wait, what? The point here is that these are inertial frames of reference. So the moving frame, the stationary frame is our station, whatever frame it is. The moving frame is going to be moving relative to the stationary frame, but it's going to be moving in a straight line at a constant speed. So the fact that it's moving in a straight line at a constant speed means that we lose no generality by saying that straight line is the x-axis. We can call it the y-axis, we can call it z-axis, we can call it the Tom axis. So I don't call it whatever axis you want, but by defining the axis, we don't lose any generality because it's not changing direction. So in these transformation problems, we always just choose, well, we don't always. We choose a single axis and stick with it. Choose a single axis and stick with it. Most often we choose x, Doesn't change any generality to call it y. Okay. So this is what's called a transformation. This is what, oh, stop it. Okay, this is what's called a transformation. We're transforming the position variable from one frame of reference to the other frame of reference, from the stationary frame to the moving frame. And this is what's called the Galilean transformation. It's the Galilean transformation, or the Newtonian transformation. This is Newtonian transformation. This is Newtonian physics. This is what Newton would have said, is that if you're moving at a certain, if you're at a certain, we can turn this into motion, right? If you're moving at a certain velocity relative to one frame, you're going to move at a different velocity relative to another frame. Anyway, this is the Galilean transformation. Let's look at, this is the position transformation. Let's look at the velocity transformation.